the institute needs to be renamed the geology, biology, and yeah, they're down to one scientist.
Not so much delay this time.
Yeah, just like that. I mean, for the intro, do you want the splash screen up, or do you want this thing up, or?
Yeah, if we can go splash, and then just switch up. Great, awesome, thank you so much.
You're gonna do a little like intro sort of thing?
Yeah, I'm gonna start it at
Time for settings, so what we've been doing is on Jeff Marcy's the observations, looking for narrow-band wave lines both on the source and off source. I'm not sure if there are still a problem. And we're also doing, looking at when we're starting the program, looking at capital curves to see, you're going to be at the Tucson meeting and EBI like mid-March. We can talk colleagues theories about what sorts of orbital
We're just going to wait a few more minutes. People are still kind of trickling in from lunch, so we're going to give it about 5 more minutes, and then we're going to get started. It's something that kind of got glossed over. We haven't really gotten the opportunity to tell everybody. The logo that we chose for the conference is actually the night sky from last night. If you were to look up at the stars, that would be what we see. That's kind of our new branding thing for the opportunity for the conference. We wanted to kind of bring in something that would show kind of our local night sky and kind of tie it in locally. I guess we'll go ahead and get started. My name is Jack Lightholder. I'm actually the co-chair for the conference this year. So thank you everyone for coming out. We really appreciate everyone who's flown in for this, or everyone who's locally coming in, spending the weekend with us here in beautiful Tempe, Arizona. I also just want to make one quick reference to, just on a more administrative note, anyone that has the program books, if you've seen any confusion between that and the website, we actually had a little logistical glitch. The program book, the two rooms are switched. So we will have an addendum that's coming out, but the website and the room pieces of paper are the most accurate for what's going on. We're just kind of going forward from here. So that being said, we will start out. We're talking today about scientific computing. We're at an amazing time in society, a point like no other in history, that we've never had the capability that we do now to be able to do analysis and do research in a way like no other. Just 20 years ago, we could never have even imagined where we'd be now. The computational ability, hundreds of thousands of times fold on data processing rates, computational ability, memory storage. It opens up a whole new world for scientists on how we can really change how we do research, what we can research, and take a different approach to analyzing science and coming at it from a different angle that we never before could. So here we'll have a group of scientists that are working through computing to change the scientific realm. I'm here to introduce our panel. We have Dr. Eric Korpella, a research astronomer at UC Berkeley. We have Dr. Travis Desell, an associate professor and assistant professor and developer of the Milky Way at Home project at the University of North Dakota. Dr. Eric Driver, one of the developers for the Number Fields at Home project. Dr. Gregory Tucker, another developer on the Number Fields at Home project. And Dr. Radim Vanco, the administrator of the Asteroids at Home project. So with that, I would like to welcome to the stage Dr. Eric Korpella.
Don't applaud until you've heard me. As I said, or as was said, my name is Eric Korpella, and I am the project scientist of the SEDS at Home project. It's It's run out of the University of California, Berkeley Space Sciences Lab, and it's been around for a while. I want to just point out, and I do in most of my talks, that I am not part of the SETI Institute, even though we're doing SETI. The SETI Institute is just like any other research organization. It just happens to have SETI in its name. Back 20 years ago, it used to do SETI, but when the NASA astrobiology boom took off, it started hiring more geologists and biologists and paleontologists and a lot of other things. Right now, the SETI Institute, even though they have control of a radio telescope, has very few people that do SETI because the funding is so hard to get. And at Berkeley, we have a lot of SETI projects that we somehow manage to keep going, even though we don't get funding for them. So, let me go grab my slide control. So SETI at Home's been around for a long time. We started building SETI at Home in 1997. Despite rumors that keep on going around, it is not the first public distributed computing project or the first public science project. That's even weirder. GIMP, the Great Internet Mesern Prime Search, has been around since 1996, so they've got us by a little bit there, and they're still around. And the longest public science project is the Christmas bird count, which has been going since 114 years ago. That would be 1900, I think. It'll be 114 years this Christmas. What the face of SETI at Home is most famous for is our screensaver. So the initial problem that we were trying to solve with SETI at Home is we get lots of data from our radio telescopes, and we were trying to develop, or the amount of processing we can do is basically limited by the amount of processing you can put near that telescope, usually 1 or 2 computers. After a while, we started using distributed computing locally, where we'd have bunches of computers. We could do a little bit more processing, but we were still pretty restricted. We were trying to come up with a way to do some really neat and new types of searches that couldn't be done even with the special purpose supercomputers that we were building for this process. So what did we want to do? Well, as a transmitter on an alien planet moves as the planet rotates, its Doppler shift will change. And so we wanted to adjust for all the possible changing Doppler shifts that you could have. That basically multiplies the amount of work you need to do by the number of Doppler shifts. We also wanted to look at, not for just very narrow band signals, but for things that were broader band. We also wanted to look for signals that, as the telescope moves past a point on the sky, the signal would get strong as it got close and get weaker with a fairly Gaussian profile for a constant drift rate. So we could do Gaussian fitting, we could search for repeating pulses, and recently we've started using autocorrelation to find generic repeated waveforms in our data. And all of these things were things that we couldn't do before. And recently, well, not really recently, the last 5 years or so, we've been running a project called AstroPulse, which searches our entire band 2.5 megahertz wide for broadband pulses that get dispersed by the interstellar medium. Because you don't know the distance to a pulsal source of radio emission, you have to correct for all possible dispersion, and again, that takes lots and lots of compute power. How does it work? Well, originally in SETI at Home, we just wrote something to break our data up into little chunks, and then when the data came back, it would just record the answer, or the results came back, it would record the answers to disk. That was great as long as you didn't want to make any changes to anything. So after a while, we came up with the idea of building a general distributed computing platform, which we call BOINC, the Berkeley Open Infrastructure for Network Computing, that would handle all of this, the infrastructure would handle all of the tasks that you need to implement a project like this. And the rest of the people talking here today are using this infrastructure that we developed for their projects, and they will tell you that even with all the pieces, it's not as easy as it sounds. So the way it works on SEDI at home is the data comes from Arecibo. We break it up using a work generator into little chunks. Those go to a download server. Our volunteers sitting over here, a few 100,000 of them, talk to our scheduling server. It tells them, go get a chunk of data from this server. They process it for a while and upload it to our upload server. Those results that are uploaded go to a validator where they're checked to make sure that they're correct results. For SEDI at home, we have them run each chunk of data twice and compare the results. It turns out to be a pretty good way of finding problems. And then an assimilator stores those results in a database. And then when we find ET, the Nobel Prize Committee is awarded, or is contacted, and they send us a medallion about that big around. Hasn't happened yet. The other stuff is details of how that works, and just know that it does, and then you don't need to worry about the details. So where has volunteer computing gone since we started in 1999? Well, the average computer is 400 times faster. The cores themselves are about 100 times faster, and there are 4 times as many cores in a typical computer. We can now do general purpose computations on GPUs. GPUs can be 20 to 1,000 times faster than the processor in your computer, depending on the type of work you want it to do. They're very good at adding large clumps of numbers together. They're not very good at doing random things on data sets. And there are now billions of mobile devices in the world with more compute capability than the computer I had in 1999. I just got this a couple of days ago. 450 megaflops, which is not bad. It's not that long ago that my desktop computer was 450 megaflops. And some of these devices have GPUs on them, and we haven't even started thinking about how to use the GPUs on, or at least I haven't started thinking about how to use the GPUs there. Typical home internet bandwidth has gone from 14.4 kilobits per second to greater than a megabit per second. And internet backbone connection speeds have increased by a factor of 10 to 100, depending on where you're connecting. What's next? One is a radio telescope can generate tons of data. We want to send that data out to our volunteers as rapidly as possible. Right now we use FedEx to get the data from Arecibo to Berkeley because that's the cheapest wide bandwidth method. It would be nice to have something better than that, and maybe we could somehow implement direct source to compute node communications. One is mobile devices. I mentioned them, but we haven't found a way to get people interested in signing up to use their mobile devices, and so far it's only phones and tablets. No one's even developing things for DVRs. And there's lots of processing power, but not a whole lot of interest. Is there a way to allow nodes to talk to each other directly and efficiently? Right now we don't have that in BOINC. And then there's a problem with cost. It may not seem like it costs a lot of money to ship data to volunteers and have them ship things back, but the development, you need people to develop the server-side software. You need servers on the server side. Those cost money. It turns out that SEDI at home is the most expensive instrument we've ever developed, well, for ground-based use. And I think that's the end of my talk. I hope I didn't go too far over 10 minutes.
Next we have Dr. Travis Desell.
All right. All right, great. So I'm Travis Desell. When I was at Rensselaer Polytechnic Institute, I developed Milky Way at home for my PhD, and then recently I moved to University of North Dakota, and since then I've kind of continued working on volunteer computing projects and big data things in general. So time pending, I'll talk a little bit about a lot of the techniques that we use to do for Milky Way at home, kind of equally applicable to like a broad range of sciences. So the important thing here is, if you get involved in the right areas of computer science, basically, you know how to use databases well, you know how to do distributed computing well, and you know machine learning, then you can basically work with scientists to your heart's content on pretty much anything you could possibly think of. So I'll start talking about Milky Way at home a little bit, because that's probably the most applicable. So just to get an idea of what you can do with volunteer computing, this was most recent. I got this last night. Milky Way at home is currently running at about 24,000, 22,000 users, depending on what statistics site you go to, and about 35,000 active hosts. So that's 35,000 computers that we got for basically the cost of a $6,000 or $7,000 server. And this is running at around 450 teraflops, which if you go to top500.org, this beats out a lot of supercomputers out there. The funny thing is that when we started Milky Way at home, RPI had just spent about $100 million to get a Blue Gene supercomputer, and it cost another $1 million a year just for energy use for the whole damn thing. We're doing Milky Way at home, and I think the entire Blue Gene goes at about 90 teraflops when we got it. So if you think about the cost compared to doing this work on the Blue Gene compared to doing it with volunteers, it's pretty dramatic. The other thing is that once they install the Blue Gene, how fast it was is basically flatlined, whereas our volunteers kind of continually upgrade their computers with new GPUs and new things like that. So we don't have to really pay to upgrade things too much unless we need to buy a new server. So that's really, really nice. We reached 1.6 petaflops at the time, so we're like the third fastest computer in the world because we were the first volunteer computing project that used GPUs to a great extent. So basically everybody who had one and wanted to use it hopped on over to our project for a while. Since it died down as more projects have given GPU applications. So most of our work, most of what Milky Way Home does is through GPUs. Really cool is that the first GPU application that was used at Milky Way Home was user contributed. So basically what happened was we had a bunch of volunteers tracking to see what computers were doing what work, and one was generating results about 50 times faster as anybody else. So everybody was crying and complaining that this person's cheating and doing something wrong. Well, it turned out the results that they were sending back were actually valid ones, and he had just made his own GPU implementation of the Milky Way Home application, and that's why it was so much faster. Turned out he was a graduate student somewhere in Germany, and we ended up co-authoring a paper with him because he let us use his code, and then I developed some code for NVIDIA GPUs. And at the time, we got some pretty massive speed-ups. The GPU version of the Milky Way Home application can run 20 to 100 times or more faster than a regular CPU, which is pretty great. So, what on earth is Milky Way at Home doing? A long time ago, in a galaxy not so far away, the Milky Way, a bunch of dwarf galaxies kind of came by. And what happened was the Milky Way was bigger than these dwarf galaxies, so it essentially just ripped them apart. And as over time, these dwarf galaxies got ripped apart and made this like halo of stars around the Milky Way. So if you look at this figure down here, I think this is, though, an artist's rendition of this, what happened to the Sagittarius stream after the Milky Way got done with it, or at least it's still beating it up right now. So there's actually bands of stars that wrap around the Milky Way making this halo. What's cool is if we can figure out what this halo looks like, what the distribution of stars are, we can probably get a better idea of dark matter distribution of stars in our own Milky Way. If you think about it, another way of thinking about it is, if you look at another galaxy, it's so damn far away, it's essentially flat. You can't get any real information about how far individual stars are within that galaxy just because of the astronomical distances involved. Pardon the pun. But since we're inside the Milky Way, we can get that three-dimensional data roughly about how far the stars away, which allow us to fit three-dimensional models to these structures that are around and within the Milky Way. So we took data from the Sloan Digital Sky Survey. This figure's a little bit old. I think there's been another version of the Digital Sky Survey since then, which has about 230 million objects, or stars. And at the time, it basically had done most of the northern hemisphere. Right now, we're on Milky Way, when we're starting to analyze data that's coming through the southern hemisphere. So a ton of data, basically points for where every star is in the sky and an estimate of about how far it is away from us. The model we're trying to fit, you can think of, if you slice up the sky into wedges, we're trying to fit cylinders in each of those wedges and then piece all those wedges together to form the streams that make up whatever dwarf galaxy got ripped apart. Another way to look at it is this. We got the galactic center, we got the sun somewhere in the Milky Way, and then we got these kind of streams that wrap around the Milky Way galaxy. And our wedges are coming out from the sun, not the galactic center, so we have to do a lot of kind of interpolation to figure out what's where, which is a lot of fun. The problem with this, though, so we've been doing this for quite a while, and we've found a lot of results about where the streams are. The problem with this is it's just where they are. We don't know how they got there, where things came from. So recently, we've kind of expanded Milky Way home past this maximum likelihood fit, three-dimensional fit of the Milky Way to determining how things got there. And the way we do that is through n-body simulation. So basically, we're running, whenever you grab an n-body simulation piece of work from Milky Way at home, you're actually running an evolution of some dwarf galaxy getting torn apart by the Milky Way. And then when the simulation ends, we basically say, well, we know here's where the stars are in the sky. How well does this n-body simulation fit what we see in the sky? And we do that over and over and over again, tweaking the parameters using different evolutionary algorithms to try and get the best fit, which should hopefully let us know how these dwarf galaxies got to be where we see them in the sky now. Also, interestingly, we don't just simulate in our n-body simulations stars that we can see. We're also simulating bodies that can be dark matter. So we'll do like a bunch of dark matter bodies and a bunch of star bodies. We'll run a simulation and then see where the light ones are. So that'll also help us get a better idea of what's going on with all the dark matter out there. So to get an idea, we'll display. There we go. If that's the Milky Way in the center there, here's a couple dwarf galaxies. So this is one of our simulations. And over time, everything's spinning. So the galaxies kind of get these bands that kind of rip apart. And this is how the halo around the Milky Way is going to form. So you get these kind of weird pulling apart phenomena. So we're running on our 22,000 volunteers just millions of simulations over and over again to try to figure out what simulation we can run that best match what we see up in the sky. And then eventually we get these nice string bands that come across like that. Okay. And so far we're getting some pretty good results with this. It looks like I'm about out of time, so I'm going to skip all the rest of my slides so you guys aren't here listening to me talk all day. Thank you.
Thank you. And then next we have Dr. Driver and Dr. Tucker from Number Fields at Home.
Testing. All right, I'm Eric Driver, and this is my colleague, Greg Tucker. I'm the chief scientist for Number Fields at Home. It's one of the point projects that Eric Korpella was telling us about, and similar to the project that Travis is working on, except ours is more mathematical in nature. So just an introduction here. So it's a volunteer distributed computing project. It's basically BOINC. There's the URL of our project. Some of the interesting stats. We've been running for about 2 years now. We currently have 2,200 volunteer host computers, which I guess is much less than what Travis has. And the total compute time to date is approximately 1,600 years. And so what I did there is I took all the times that came back from all the hosts and I just added them all together. And so that's a lot of time. If you had a single computer at home, that's how long your computer would be running to get the kind of results we have. I think we're sitting right now at about 8 teraflops, which is pretty powerful. So just a quick description of our project. It's, like I said, it's mathematical, and I think most people are here for more of the scientific computing stuff, so I'm going to go over this pretty quick. What we're finding are mathematical structures called fields, and we're trying to categorize them by special properties called their ramification properties. We are currently working on degree 10 fields, and the lower degree fields I actually did for my PhD dissertation. I developed the algorithm for finding these. And when I got to, I wanted to do degree 10, but I realized that it was computationally just impossible on my single computer. So then I was talking to my friend Greg here, and we went to school together. And he's the one who actually introduced me to BOINC. I hadn't even heard of it before then. And so that's what got this all going. And worked with the math department at ASU, so this project is based here. And they got us a server, and I set this thing up, and that's pretty much how that got started. But anyways, we are currently working on degree 10 fields. What it does is, given a set of prime numbers, we find the imprimitive fields that are ramified at those primes. And this set of fields is finite, and that's what we're trying to find. We all have a second part of the project, which is also to categorize the fields by their discriminant. And so we picked about 1.2 times 10 to the 11th. And we're trying to find all fields with discriminant less than that. And that has certain applications to a certain group of mathematicians. So real quick, the applications for this project. Most of them are mathematical. I would love to talk about these in more detail if you'd like. If you want to talk to me after, after this, if anybody's interested in the map, I would love to talk about it. But I think this is too much out of what we're trying to do here, which is scientific computing. So I'll just mention it real quick. There's things called automorphic forms. It's related to what's called the Langland's program. These are very abstract mathematical theories right now. So at this point, probably not a lot of use for this, practically speaking. There's something else called arithmetic statistics, where this can be used. Also, a lot of your cryptography algorithms use number fields. And so this has some potential uses there. There are also some remote connections to theoretical physics, something called p-adic quantum mechanics. And I don't know a lot about the physics stuff, but I've heard that there are these connections. And there's also some connections to string theory. And that's actually via the automorphic forms, which I mentioned above. And then with that, I'm going to turn it over to Greg, and he's going to talk a little bit more about some of the computing challenges we had.
Thanks, Eric. So yeah, as Eric said, this is we was here. It's a local project, and I've been lucky enough to be start from the beginning with Eric on this. And before we went public, we had quite a bit of time when we built up our Boeing project, and we're lucky enough to have all Eric's contributions from Boeing to get us started. And all the infrastructure is terrific in this Boeing project, but we still have problems, of course, and that was part of the fun, is trying to figure out problems with starting our own Boeing project. And so this is just a few of the list that we went through. And not only we rely on the volunteers to help us with the crunching, but we also could use some help with the project. If you guys would like to volunteer also, we could use some of the stuff that's in the bigger projects to help us with promoting that to a wider audience. But basically, it's highly math-oriented, of course, and we rely on these peri-libs, these libraries of mathematical functions, and they're hard to port, we found. And they don't lend themselves really easily to GPUs. It's probably possible, but we haven't had a GPU project yet. But that's another area where we could use some help. If people want to join the project and help us with the GPU port, that would be terrific. But so far we've ported to a smaller number of CPUs. We also, just to give an example of the problems we've had, we found a way to break up the application, but we couldn't tell how long our work units are going to run. It's a fairly simple way to break it up, and a way that we could get work units to run about an hour or a couple hours. But because of the fundamental properties we're trying to find with these fields, sometimes and unpredictably in a really short work units, like a second. And that kind of wreaked havoc with the credit system that we were using. So it was all a learning process. And also there's these other cases where we're trying to factor polynomials, and sometimes they rely on the edges of what can be done simply, and it explodes, and the thing crashes in these rare cases, and you have to track down and try to rerun them in different ways. Yeah, that said, it's been quite fun helping Eric with this project, and we need more volunteers. We could use a screensaver too, we don't have the visuals, of all of what it look like, and these other projects have screensavers. So if you'd like to volunteer and help us with the project, we would love it.
Great, thank you. And up next we have Dr. Radim Vanco with us all the way from the Czech Republic. Hopefully in a couple years we'll be doing that, right? Great. Dr. Radim Vanco.
So, hello everyone. My name is Radim Vanco, and I am the scientist and administrator of Project Asteroids at Home. Aim of our project is deriving physical properties of asteroids from photometric data, which are finding period, shape, and the direction of spin axis. The project was founded by Charles University in Prague and Czech national team jointly. And I forgot English language is not my mother tongue, so I would like to apologize for my English. So, why to study asteroids? It's important for many things. For example, learning more about our solar system. For example, if we are in future to send, for example, mining probes to some asteroids, we have to know the shape and more information about the object that we would like to send them. It's also important for understanding the origin and evolution of our solar system. And also, thermal emission of small asteroids can be significantly change their orbit, which can be crucial for predicting the probability of their collisions with Earth. Many of data we have are from the main asteroids belt, which is located here. What is light curve photometry? Photometry is the process of measuring brightness variations that are caused by rotations, and the brightness variations is called a light curve. As you know, asteroids rotate and their brightness variations changes due to scattering light from an uneven surface. So here you can see an example of such light curve, which is measured in time. You can see here that the brightness increases and then slightly decreases, and then it repeats. If we have, you can see the whole period because when you see one period and I'm sorry for that. You can just you can see the one period and the second period. I hope it's not much puzzling for me now. Light curve inversion. If there are enough light curve from different geometries, the shape model, the spin axis rotation, and the period of asteroid can be derived. The process of this reconstruction from light photometric data is light curve inversion. The main problem is that we don't have data where we would see the period directly, like I was seeing here, but we have only part of the period. On these pictures, you can see that we have, for example, this part of data, but we don't have, for example, this, and we have this part. Or on the other picture, you can see that we have, for example, this part, but we don't have this part. So we have many of the points of the data, but they are sparse in time. So we have to derive the whole fitting period, and then if we again see the periods directly, we can compute the rotation. As I said, it's very this is very time consuming. finding the period. So that's the reason why we use distributed computing. And for this, we use point platform, as you already know from previous presentation. This picture is look different than the. Oh, I'm sorry, it doesn't look like I wanted. There should be pictures of our results, but I'm very sorry that you don't see them.
The lights on?
We usually have our results usually our results which we are publishing are usually asteroids from front view, top view, and side view, and there are its parameters. So I'm very sorry I won't show them. On that pictures there are the latest results of our work, but they are also not as should they look. So I will skip that. Current status of our project is that we are processing lower data. We have data for 500,000 asteroids, and previous I forgot to tell that processing the data for one asteroid takes about 10 days. And because we have data for 500,000 asteroids, we need high computing power. So that's the reason why we need distributed computing. We have already processed 10,000 asteroids, and we have 290 new models for them. The basic results are stored at our website asteroids@home.net. Later, the results are published in peer-reviewed journals and stored in DEMIT, which is a database of asteroid models from inversion techniques. And future of the project. We would like to process all lower data and also the future data from the lower observatory. Then we would like to start processing data from pan-stars, and we are ready for Atlas Gaia and LSSD when they are operational. Also, I would like in the future create models for simulation software CSPR, and sometimes in future we would like to derive orbits of asteroids which could collide with Earth. So thank you for your attention. I hope you understand me because I had a glitch there. If you want more information about our project, you can visit website asteroids@home.net. You can also contact me via email, and that on the website there is also a link to DEMIT where you can see more detailed information about our results. So thank you.
Great, thank you everybody. We'll go to questions from you. We'll go with questions from the audience now. I guess if everyone wants to just come up here, and if anyone has any questions. I'll kind of start off just by adding a note. This is really something we can all participate in. I found this a couple of years ago, and it's really as simple as downloading a program. You get to choose what you want to, if you guys want to come up. It's just as simple as downloading a program. You can pick what you want to contribute to. There's probably, I would say, maybe in the 30s to 40s of projects now from around the world, different types of science. it's really a way to leave your desktop when you go to school, and it's solving simulations of asteroids or curing cancer or working towards some type of scientific objective even when you're sleeping. So it's a great way to kind of spread. We're all in a science major because we want to make that contribution. So it's really a way to maximize your time even when you're sleeping. You're helping. So it really is that simple. I guess I'll start off with a question. We kind of talked briefly about it. The challenge of working with the public. It takes the challenge with the scientists from going and writing a 100, 200-page proposal to the National Science Foundation or to NASA to fund this research. And instead of doing that, you're kind of applying it to the public, and you're trying to really reach out to the public and convince them that what you're doing is worth them funding and them spending the energy on and keeping up the computers and all that. How have you guys all worked through that, and kind of how do you interact with the public, and what kind of challenges have you guys found with that?
I guess I'll all right. So I guess I'll go first. It's actually, for me, it's actually been really cool. In one sense, volunteer computing is a lot like democratic science. Like, where else can you personally vote on what science you think should be funded or researchers should be working on? Well, if you have a desktop or now mobile phones for some projects, you can basically say, I like this research, I'm going to donate my computer to that project when I'm not using it. So that's pretty interesting. The one thing I've noticed running different volunteer computing projects is probably the most important thing is having to go out there and talk to the volunteers about what you're actually doing. They really want to know what the science is going on. So if you don't do that, they tend to go away. But if you keep giving them information, that keeps them coming back to the project and participating. On my end, that helps keep me and the other researchers honest, because if something breaks, I'll get a bunch of emails in the middle of the night like, the project's not working, and so it keeps me working at a pace probably faster than I would if I was just running something on a supercomputer, and if it didn't work, oh, it's not really bothering anybody. So I have a lot of kind of public users keeping me in check and keeping the project up and running. That really kind of make it an interesting dynamic. So in some sense, my boss is the users as opposed to anybody else.
Problems always happen on Friday at 5 o'clock.
Or when you're at a trip.
Yeah, if you say fly to Phoenix, then you'll get email about all the problems that are happening while you're gone. We've actually found it very useful to have volunteers who act as essentially emissaries of the project, and rather than me having to draft an email on Friday afternoon explaining what's happening, I can give a 3-word explanation to one of the volunteers who understands those 3 words and who can turn it into something that everyone can understand. So we rely a lot on volunteers for more than their computing power. We rely on them as, in addition to keeping us, letting us know that there are problems, we rely on them to solve problems on their own. And let us know if there's an issue that's showing up in the forums. None of us have time to read all of the threads that happen on our user forums, which are a big part of Point. They let the volunteers form communities, but yeah, if a problem goes on there for a week before we hear about it, that would be an issue that we want to take care of sooner.
I think this is actually one of the parts of it that I least enjoy, and that is trying to get all these other people interested. Because I'm interested in the science, and it is very difficult to attract the volunteers. It's like, I'd rather be doing the science, not social media. But one thing that does help are the posting news items. It makes it look like your project is alive. We do other things like challenges. You issue challenges and then the teams get involved. And our project, we more than doubled our teraflops when we were part of actually it was issued by SEDI. It was a team challenge. So SEDI initiated a challenge, and then all the other teams jumped on, and they were all competing to see who could get the most credits. And that worked really well. But is there something you want to add?
Sure. Yeah, I agree with Eric that So we found that some of the volunteers knew more about the link than we did. And they would tell us that you have a problem with this and you need to go fix it. And they'd show us, where would I find it. And it was sometimes hard to, understand their motivations, when it's just credits and you get nothing for the credits. But once you join a project, you can see sometimes it's kind of addictive. Where your ranking is in the list. And it is part of a community. And volunteers are important in many ways.
Did anybody else have any questions? No questions? Question.
So you're all using this sort of distributed, the at-home systems. Would you say that like traditional supercomputers are just kind of dead now in the sciences?
I would say definitely not. This distributed architecture is really only good for a series of problems that are known as embarrassingly parallel, meaning that you can break them up into tiny chunks, and if you do one tiny chunk, you've made progress. There are a lot of, like climate simulations. Home computers really aren't to the point where you can do a whole high-resolution climate simulation on one. So, for example, climateprediction.net, I'm not even sure if they're still sending out work at this point, but they were doing low-resolution climate simulations, but lots of them. So the climate modeling that is probably of most interest to typical climate scientists is the stuff that runs on a supercomputer and has the highest possible resolution. And you just can't do that as easily with one.
Anything?
No, on the head basically. That's nice. So there's a lot of problems that you can do with a volunteer computing project, but there's a lot you can.
That brings up a good point too about the difference between kind of a centralized system versus a distributed system. You guys want to talk maybe about the cost? I know we were discussing it last night at dinner actually, that there's a cost associated either way, and some systems probably have better ways of doing one, because you do still have to send all this information over the internet, which has an associated cost, versus maybe $1,000 or multiple thousands of dollars per hour on a supercomputer, depending on how super your computer is, I guess. You guys want to talk about the differences maybe in running these simulations versus having to buy supercomputer time versus the cost of sending it over the internet?
You'll probably get different answers from everybody else, but like I said in the beginning of my talk, we initially were running a lot of the stuff we're doing at Milky Way at home on RPI's Blue Gene, which is many orders of magnitude more expensive than running Milky Way at home. We don't have to pay for our bandwidth, so that helps a lot. I have gotten a lot of nasty emails from the IT services for a while there when they didn't really know what was going on with the project. So we'd start looking at a new area of the sky, and we'd have to send out 20 to a 50 meg file, which isn't that big, but we'd have to send it out to 20,000 people, and they'd be like, "You guys sent out a terabyte of data this week. What on earth's going on here?" But we didn't have to pay for that. So for us, Milky Way with home was a big win. Significantly cheaper than running things on a supercomputer, and automatically upgrading, the users automatically upgrading things. So it's great for us. But yeah, when it's $1 million a year just for energy for a supercomputer.
See, I approach it from almost exactly the opposite, because when we turned on SEDI at home, we went from being non-existent to being the largest user of the internet in the University of California system. We were up around 100 megabits per second continually, and at that point, the University of California was paying $600 a month for every 1 megabit per second. So they basically kicked us off the university's internet, and we had to find our own. And we're still paying for our own, even though now we're still only about 100 megabits per second, and we're a small fraction of the university's bandwidth. We're in negotiations with the university to go back on the university's paid-for system. Whereas for supercomputers, we've got several supercomputer centers in California, and the UC, in some cases, is involved in the administration of those, and we often get supercomputer time for free. So it's not really applicable to what we do, but it's all a question of what your university is willing to support, I guess, and what it's got available at its disposal.
One thing I'd like to add is actually anybody in this room with a computer who knows something about Linux, you could actually do your own server. My first server, I ran it out of my home through Cox. I set up the URL so I didn't even have to pay Cox anything extra, just the standard internet account. And it's just my first one was a Core 2 Duo. I think it was a Pentium. I only had 24 volunteers. It was kind of private. I only told a bunch of friends and family. So I had about 24, but you get some computational power there. The point is, if you know anything about Linux, you can do this yourself at home.
I guess really what it comes down to is it's another tool for scientists to be able to do more science and use another avenue to accomplish more of these tasks rather than waiting on the National Science Foundation to fund something or NASA. It allows people to just go out and do it. Anybody else have any questions? Go ahead, someone.
Is there a way to, like, if I use Linux pretty much only, if a bunch of us were to just do the same thing as you, then would ours link automatically to, basically everything on our server would link to your server and multiply? If we were to just set that up for, like, a bunch of my friends on campus would do the internet.
Meaning setting up a server to, do you have a project in mind?
No, I'm just saying, like, is there a way that like we could set up a server and feed it into your server? If you
I think from a volunteer perspective.
Yeah.
So basically, if you want to do anything with any of these projects, if you go look up Boink, you can, or go to any of the projects, you download a piece of software.
I just mean, like, is there any computational advantage to feeding servers into your servers? Multiple processing in a single computer?
So actually, a lot of the applications on different projects will run stuff on multi-core. So you can download different versions of the applications and look at that.
But for example, a cluster would, in general, a cluster for this kind of thing is no better than the individual nodes, each acting on its own. In fact, that's what it usually turns out to be. You have to hook a cluster up to Boink, you have to write some software that portions out the work you receive to the nodes, and you might as well let Boink do that on its own. So I don't think there's any advantage to pooling like that.
I do believe that the servers too have an additional error checking, right? That a lot of the applications are actually optimized for the home user, so they're actually optimized for kind of a normal desktop as opposed to any type of server platform. That way people can volunteer at home. I actually have a very similar setup at home to what you're suggesting. I have a server rack, but it's all regular computers inside of it. So it's a 15U server with 4 regular computers sitting inside of it. So it acts similar to a server in the physical capacity as opposed to desktops, but it's still running on like a regular just Windows operating system. Any other last questions?
Yeah, one here. I can't remember which slide it was on, but there was a bullet that one of the tasks was cryptography. Would you all say some more about what that is and what you're doing?
So what we're doing is really just computing number fields. The cryptography is an application to the number fields that we're finding. And at this point, I can't really say that we have an actual application. all I can say is that cryptography, some of the modern cryptography algorithms are using number fields. And so by having some more knowledge about number fields, there's a potential to help with cryptography. Does that answer your question?
Yes. Optically, or how do you handle data coming in of different sizes, format, or do you just run single? How does it work from the observations to? Because I know I do both radio and optically. I do the photography also, but I only got one chip. I don't have to mess with a bunch of for distance.
Yeah, it's each project has to write the code that does that on their own, and that either will, both on the server side and on whatever applications they're sending to you.
Or like optically, do you have to change your coding to handle different observatories?
So basically, when we get the data from Milky Way at home, it's already been like processed by a lot of astronomers. So in a lot of ways, what we're actually dealing with is we have a flat file, which is just like an X, Y, Z, and maybe like so when you look at a star in the sky, it's kind of far away, and you just have a point to deal with. So how do you know how far away that star actually is? So it's kind of a guess. So we have like an X, Y, and a guess for the Z, and that's pretty much it for our data file. So we don't have to do a lot of that processing. It's already been done by astronomers and things like that.
I think we're going to have to wrap it up. Our next talk in here is going to be the Space Elevator Technology panel. I think we'll all be around afterwards if anyone has any additional questions. We get another round of applause for our speakers.
That works.
All right, awesome. Thank you guys all for being here. You are at the space elevator talk right now. So if you're looking for commercial space, that's over in Armstrong Hall, but we're glad you're here because it's going to be a good one. It's my huge pleasure to introduce Drs. Peter and Kathy Swan, renowned authors, distinguished military veterans, who provide a lot of insight into the feasibility of this technology. And presenting with them today on this panel of space elevators is Mr. I apologize. I just Skip Penny. I am sorry about that. Who is the Vice President of the International Space Elevator Consortium. They put together an excellent presentation that's going to talk all about the feasibility, some of the things that are still hindering us. So without taking up too much of their time, I'd love to hand it over to them and let them do their thing. Also of note though, don't save your questions for the end. If you've got something that comes up, throw your hand in the air and they'll get to you right away. Thank you.
Thank you, Ben. Michael Lane was supposed to be here, but he had a family emergency, so he couldn't make it, and we're sorry, because he's really the thrust behind the lunar elevator. We will get to that, though. He gave me some slides, so we will hit lunar elevator. But the three of us are focusing on the Earth elevator, and we'll be talking about this today. It's a very simple, straightforward agenda, basic concepts. We'll talk about legal and policy, a concept of operation, technological feasibility, lunar elevator, and we'll summarize it. Now, we're members of the International Space Elevator Consortium. Student membership is very cheap. Okay, you'll see WW later. But anyway, it's an advertisement. But I'm just letting you know what we've done lately. We've published 2 reports here. One on space debris, which everybody asks about. We'll cover it real quickly. One on concept of operation. So, I'm hitting the wrong buttons. Anyway, so we've got those, plus we have a journal, and then we have a big report coming out called Space Elevators, Feasibility of the Future and the Way Forward. This is 350 pages technical. Now, you guys are all students, right? You expect that to be $300. $19.95. We want to get it out. It'll also be a PDF file or ebook or something. Coming out in the next month or so. But anyway, we're going to leave these flyers out there. If you're interested, you can grab them. I'll bring them around tomorrow and stuff like that. Okay, let's start to talk about space elevators. What's the concept? I love this little diagram. We've got a resident artist, Frank Chase, and he does these things for us. We got the marine node at the bottom. Bring our payloads there. Load them on tether climbers. They go up to the geo node. Then you go off beyond the geo node to release. They go to the moon and Mars and everything in it. No chemistry required. You just go up there, get added velocity with the rotation, let go, and you go to Mars. No chemistry required. You can go up to the apex anchor, and that's a nice sitting place, good view of the world and everything else. Science could be done there, and you can release from close to there to go to the further planets. And you can use gravity assist and essentially get out of the solar system. No chemistry required. So why are we doing space elevators? It's basically a simple concept. String, rock, throw it around your head, tension, ball stays out there, same concept. Then you have opposing wheels on each side of a 1 meter wide tether. Pressure, friction, electricity, right on the... No jokes about elevator music for 2 weeks, okay? We're going to talk about that. But anyway, but it's a very simple concept. So let's take a look at the next one. Where did it come from? Well, there's a Russian, Yuri Aksunov, and an American, Jerome Pearson, who came up with the ideas. They recently sat down together about 2 years ago at our conference in Seattle, and they compared notes, trying to figure out who stole whose idea, right? It turned out neither one had any common denominator, so they agreed that it was co-invented. And that's because during the time period Yuri did it was the Soviet time period, and they didn't distribute information very well. So Jerome came up with it on his own. Jerome and Arthur C. Clarke spent a lot of time talking, and Jerome wondered why he was calling them. And then Arthur C. Clarke came out with a book focused on the construction of the space elevator. So that was kind of interesting. But why are we doing it? Well, you guys are here. You guys are students. You're going to be alive for a lot of more years, and hopefully we're going to use what I call the space option. The resources on the Earth are limited, according to the Club of Rome and a whole bunch of other people talking. What we want to do is go out into space, bring resources back for humanity. Okay, space mineral resources. There's going to be a phenomenal answer to some issues on Earth from outer space. So the space elevator is going to make that work. And how's that going to work? Daily launches. Anybody know how many launches we had last year around the world? Around the world, take a guess. How many launches did we have to space? Okay, everybody who thinks it's more than 100, raise your hand. 100 launches. One every 3 days. 85. 85 launches. How much can you put on a rocket? What, 6 tons at the most nowadays? Sure, you can wait for the heavy lift guys later, but you know, we're not talking about very much. Times 85 launches. The idea here is 14 metric tons of payload, 6 metric tons of structure, and going for $500 a kilogram. How much does a kilogram cost to get to GEO today? If you said $20,000, I'd agree with you. We're going to do it for $500. Okay, so now I'm going to transition to Dr. Swan, the younger. She always likes
much
yes.
younger. Yes. So I'm going to talk about the boring parts of this whole thing. The technology, the hopefulness of it, all of that is terrific, but in order to make it work, you actually have to have something that works within the policy and legal regimes. So one of the reasons for our design is that you have to get some sort of a basis for what you're doing and what you can do. Yes, we believe it's going to be commercial, but I don't think that anybody in this room believes that it can be done just commercially. You have to have some government sanctions, whether the government is an entity, a state entity, or United Nations sorts of consortiums, doesn't matter. But you have to have someone sponsoring you because